Here we are in our quest of physics lab, playing with the toys while there's no students here. And here we have our free fall tower. We dusted it off with the help of Mark and Dr. E. And now we're going to go ahead and test the falling rates of different objects. So do all masses fall at the same rate? Well, that was a question posed by Galileo a long, long time ago. So here we have a penny and we have a feather. And we're going to take this penny and feather and we're going to put it in our tube, our little free fall tower. And we're going to seal this tube. And as you may have come to the conclusion, there's still a lot of air in this tube. Okay, so I put those in the tower and I think we still have air in there. So let's see, which one will fall faster, if any? Well, if we have air in there, clearly we can see that the feather doesn't fall as fast as the penny. What's going on? So Galileo's conclusion was they fall at the same rate. So what do we need to do to make these fall at the same rate, if anything? So what's the answer, Dr. E?
Well, I think we need to get rid of the air in the tube, and then the air resistance won't be a factor, because the feather is going to catch a lot more air, and the feather is also much lighter than the penny, and so air resistance will be much larger in comparison to the force of gravity on the feather, and that'll cause the feather to fall at probably close to a terminal velocity, which will be way slower than the penny.
Now we're going to put a vacuum on this tube to suck the air out, and we're going to try a penny and a feather and a vacuum. Alright, we have a feather and a penny in a vacuum tube. I pulled a vacuum for 2 minutes. We're going to flip it and see who wins. It's hard to tell. Flip it again. Yes.
Are they falling at the same rate?
They look pretty close. Sometimes it looks like the penny wins, sometimes it looks like the feather wins.
So inside our vacuum tube, we have no air, and as proposed by Galileo a long, long time ago, all things fall at the same rate.
Now I'm going to release the vacuum. Feather goes to the top. Oh, feather came apart.
In the absence of other forces.
Now we'll try it again and see who wins. Oh, this time, penny easily beats it. We lost the feather.
Students, here we have a variety of objects to test the theories of falling bodies and the acceleration due to gravity. We have a variety of items, different masses, different shapes, and we want to explore the effects of air resistance on our falls and contemplate the question of bodies falling at the same rate. A baseball. A feather. Number 4, a rock. Ooh, frisbee. add initial velocity into our acceleration due to gravity and one-dimensional motion problems. So what goes up must come down. But the question is how far up and how long? And can we compute these values? Three. To do our weightless water demo.
I have blue water into the cup. There's a little hole right here. I'm going to fill it up over the hole. And as you see, it can come out, covering the hole now. We're going to drop it and see what happens.
And Dr. E here is going to try to catch this. And the question is, will the water be streaming and losing its volume as it falls? Hello students, here we are ready to do lab number 2 for our online physics labs. Again, here's Mrs. Call for you, and I'm going to give you some guidance on this next online lab that deals with one-dimensional motion and free fall. Some wonderful topics. Now that we have a handle on how to do measurements and agree on our measurements, the next big step is to say, what are the things that we see and observe in our universe? We see things are in motion. So we really want to get a handle on analyzing motion. And we break it down, and we'll do a breakdown into 2 different labs. First, we want to break everything down into 1D motion when we can, one-dimensional motion along one axis, horizontal axis or vertical axis. And in the next lab after this, we'll look at 2-dimensional motion. So 1D motion, a special case of 1D motion is free fall. And free fall is when the only acceleration is due to gravity. So with a lot of these topics that we're going to cover in lab, there'll be a lot of problem solving using kinematics. So our main goal is to explore 1D motion. And we want to look at vectors and constant acceleration. So we want to explore 1D motion vectors, and we want to look at special cases where we have constant acceleration. We want to explore 1D graphical relations between displacement, so vector x if you're in a horizontal axis, or y when we talk about a vertical axis, or in general, I like to use the r vector, so between your displacement, velocity, and acceleration. So it's most important we have a strong handle on our definitions. We'll be using our definitions and then also using those definitions and applying them in the problem solving using kinematics. Okay, so we want to explore 1D graphical relations. We want to explore the cases of free fall, falling bodies, and free fall. In the case of free fall, the acceleration is only due to gravity. So we want to look at falling bodies and free fall. Important to identify these, because when you identify a free fall problem, then you know it's a one-dimensional motion problem, and then you apply one-dimensional kinematic equations, which are a lot easier than two-dimensional kinematic equations. And then what we also want to do is just go ahead and apply problem solving to find the acceleration due to gravity here on Earth. So for Earth, this is approximately 9.8 meters per second every second. That's how much the velocity is changing every second. So we say meters per second squared, and we give that value a designation symbol of little g. Never get your little g mixed up with your big G. Two totally different things. So little g is the acceleration due to gravity only. Now, note, this value changes depending upon where you're measuring it on the surface of the Earth. It has to do with the variations of mass in the actual Earth. So our average value is about 9.8. Some people like to go to the next decimal place and say 9.81, but it really depends on whether you're at sea level, whether you're in Hawaii, whether you're on the top of Mount Everest, and how much mass, the density also of that mass below you, that plays a factor. So it's a very tricky value to map across our globe, so we use approximations unless otherwise we need a more specific, precise value. So something to look into. This is a lot trickier to measure on the surface of the Earth than you would think. So for our cases, anything that we do experimentally in this lab, we want to compare to this little g value, okay, which is 9.8. That'll be our approximation, our theoretical value. So we want to look at all this, and then we want to also apply our 1D kinematics. For problem solving, which you're going to have some warm-ups and pre-lab questions that will set you up to do the two main parts to lab. So there's two main parts to our lab, and part one, it will be exploring 1D motion and free fall using simulations. We have some great simulations that will help us understand a lot of the graphical nature behind the relationships of displacement, velocity, and acceleration. So we really want to know the derivative integral relations there. Then we're also going to look at like one-dimensional problems where we have cars and we compare the motion of cars. Let's say we have one that accelerates and one that doesn't. Can we find when they would meet if one car starts ahead of the other? There's a great simulation on that we have posted for this procedure on the online lab. And then we'll look at one-dimensional motion in rockets, a really fun topic. And one of the simulations that we have that is almost exactly like one of the ones that we actually do in the physical labs here in our classroom is the PVC FreeFall Lab. Okay? And in that lab, that simulation lab, what happens is we're going to drop different objects, and we're going to measure the changes in the heights or the displacement, the positions, the changes in positions and the height. So we're going to take a look at that change in position. We're going to use the change in position and also measure the time it takes to fall. And if we have change in position and the time increments, then we can use that to find average velocity, which we could then use to also find acceleration. So there's a few good labs that will be used for simulations in this case. So what we have is, we'll have graphical simulations. We'll have two-car simulations. When do they meet up? Okay. Then we'll also have one-dimensional motion in rockets, 1D motion in rockets. And then we'll have the PVC, FreeFall Lab. And we'll explore falling bodies, and when we get these measures like our delta y, okay, our change in position, or our change in the position vector, and our change in time, our increments of time, we'll use this average velocity and other values, okay, to do problem solving with. So this is a really neat simulation because it allows you to drop objects on the surface of the Earth using the acceleration due to gravity on Earth's surface. And then we're going to do one little test, like if we were on Mars and we were analyzing falling bodies on the surface of Mars, we would notice that the change in velocity will be a lot less than on Earth. So Mars has a local acceleration due to gravity, which is about 1/3 of Earth's. So you can compare those measurements. Okay, and then next, part 2. What we want to do in part 2 is have you experiment. Windy motion, free fall experiments. So what we want you to do is to collect a lot of items to compare the falling rates of those items. And we have a few good videos set up for you today that you could do that comparison with. So we know that if you take an object, and here we have it at a certain height, we can measure this with a measuring app, or measuring tape is great, or if you could use string, you can measure the height from which you're going to drop an object. And the trick here is to collect many different types of objects you could drop, right? You want to compare, maybe you have a ball, different rocks, frisbees, feathers, crumpled up paper works really well, erasers. So get a good variety of objects you could drop. We'll specify the number that we'd want in our lab, and we want to drop these from a certain height and try to get an idea of the timing here. Now what's going to happen is we're going to have reaction times involved, and this will be something that you want to compute for your error. So if I take this ball, it will drop to the ground, and I can find out how long it takes to actually drop to the ground. So if I want to look for my time, I would measure the height, and I would use my local acceleration due to gravity, and I could use my 1D kinematic equations to figure that out. So here, if I have a y value or a displacement value, I would use that to figure that out. Plug in my 9.8 meters per second for acceleration. So acceleration is constant, which allows me to use kinematic equations, and I could find out the time it takes to drop. Now, in another case, if I want to video this, what I might want to do is get a partner And instead of just trying to time this yourself with your camera, which is really hard to do, or with a stopwatch, what you want to do is from that same height, you want to measure the time it takes to drop. And in that case, let's pretend that g, little g is unknown, and you solve for little g. And what you get for that little g might be much off. So what we're going to do here is we're going to drop different mass and sized objects from a height. And we're going to measure that height, right? So what we want is y, delta y, you measure. And then g, when you use the theoretical. And then g, in one case you're going to find the experimental value. And then in some of these cases you're going to measure delta t as well, your drop time. Okay? So this is going to be 1D. And what we want to look at here is test this theory that Galileo proposed a long time ago. So Galileo says all objects must fall at the same rate. And what we know today is they do fall at the same rate in the absence of air resistance. We have a lot of air in this room, so not everything's going to fall at the same rate. However, we could go to the surface of the moon, we could drop a hammer and a feather like they did in Apollo, one of the Apollo missions, and we could see that they drop at the same rate and they hit the surface of the moon. So we all know that a piece of paper, if you drop a piece of paper, it takes a long time to fall, whereas we take the same crumpled piece of paper and it drops faster, and that's because of the air resistance involved. Okay? So if you drop a feather and a ball, we expect the ball to fall faster. So what we want you to do is to get good height. My suggestion is to get as high as you can to drop objects, drop oranges, watermelons, have a lot of fun with this and compare those values. Okay? Step 2 here is to not just drop, but to throw it up with an initial velocity and repeat the above. So now, the tricky part is throwing things up from that same level of height, right? So if you want to get as accurate as you can as a measurement, you want to try to figure out what your initial velocity is. So in this case, we could solve for a lot more different variables. So if I throw that up, and I want to try to keep it as one-dimensional as possible, and we'll show you with some demonstrations, we could get that 1D motion and the time of flight for it to go up and back down will give us, we'll get the delta t value, we could get the height value if we can, or we could solve for that as well. So we could get those values and we could use the little g to find the initial velocity. Okay, so we want you to practice doing some of that. It's going to be a little trickier, so it's very experimental. So we're going to be dropping different objects at different heights, and we're also going to try throwing up objects and computing different variables. So throw up with a V naught and repeat above. Solve for variables. And the last part of this experiment is to analyze the situation of free fall with water in a cup. So we did some practice trials, which you'll see shortly. Now, if you had a cup of water and you put a little hole in there, you fill this cup of water, let's say you put a hole in the center of the cup, and you drop this cup of water, will the water come out through the hole or not if you were to drop this? So you could see the results of that experiment in our next part. Okay, so we'll do the weightless water experiment. So, do all objects fall at the same rate? That's a big theory we want to test. And if not, we want to look at why. Or if it seems like they don't fall at the same rate, why is that happening? And if we say yes, we want to really test that theory by trying to drop things in a vacuum, okay, which is another little demo we have. So do all objects fall at the same rate? Yes, they do, but what we want to do is explain why we see these differences, like the feather versus the ball. Why are they falling at different rates? And can we analyze the different rates in which they're falling? Does weight play a role in that? So I could drop like a heavier an object like a frisbee and a feather. Okay. And what we want to explore is the role of air resistance there. Okay? Or drag, the drag force, and see what factors of the drag force play a role in our dropped objects. So that is a big question here. And then how do we experimentally find G? What are the clever ways we could find our acceleration due to gravity? Okay, and then how do we explain this water experiment among many others? So we'll show you some fun clips and demos in the next segments. Enjoy. Hello students, some key ideas behind lab number 2, 1D motion and free fall. Number 1, know thy definitions. Okay, so your definitions play a huge role in doing the parts of the lab. So your definitions are very important. This is how we derive the kinematic equation. So always remember, you could derive the actual kinematic equations if you forget what they actually are, if you don't have them memorized. So definitions we have, displacement is the change in the position vector. So that's y final minus y initial, and we'll be doing some parts that will involve that definition. Okay, and so this is for displacement. The next one is velocity, and always remember when to apply your average velocity formula from your instantaneous velocity. Okay, so in this lab we'll do a lot of average velocities, but in the case of doing instantaneous velocity, that's when we want to take our derivative if we have an equation, or take the slope of the line. All the tangent lines will give you the instantaneous velocity. So V, I'm going to just write V average here, and that's going to be delta y over delta t. So our displacement over time will give us our average velocity. And the other definition we need here is acceleration. And acceleration is A average equals delta V over delta t. So this would be V final minus V initial over delta t. There's going to be many cases we're going to apply this, especially when you're doing free fall and you're trying to experimentally find little g value, the acceleration. When this A is equal to g, that's when the only acceleration is due to gravity. Okay, so number 1, you need your definitions. Number 2, we need to know our relations. Let's see, our graphs, our graphical relations. between, and understanding the integral derivative relationships. So the graph relationships between our displacement or our velocity and acceleration. So here's an example, and the simulation should help with many of these different situations. If I were to just drop an object, like a ball or rock, a frisbee, a cup, a textbook, whatever that object is, if I were to drop an object from a certain height, what would the displacement curve look like? Well, here, if I use y to represent my position vector for my vertical positions, I'll do a y versus t, or a displacement versus time graph. So if I'm going to plot out the drop of that ball, let's say I dropped it from a height of 2 meters, then this would be my curve. That would be the height of 2 meters, and this would be the amount of time it takes to hit ground zero right here. Okay. So there's my position versus time. Now what would that look like in terms of velocity versus time? So if I take a velocity versus time graph, I'm not going to put this in units in for ease. What would that look like? Well, the velocity is changing. Okay, so if we all take all our delta v, delta y's, delta y's, delta y's over delta t's, we would get this next curve. And what's going to happen is it's going to be speeding up and in the negative direction. Okay, so what this will look like will be more like this, and your directions just depend upon how you label everything. Okay. So I'm going to and that would be a linear. So this would be parabolic or slash quadratic. And then here we have a v versus t, a velocity graph, where we have, this is linear. And here we have it speeding up in the negative direction, or in some cases we can have it speeding up in the positive direction. So it could be either one. And it just depends on how you choose your reference frames here. Now the related acceleration versus time curves would be so on. If your velocity versus time curves are linear, then taking the derivative of a linear equation will give you a constant value. So in this first case, your acceleration will be negative. So your A versus T graph would be a negative acceleration value. Okay? So this is negative, positive, positive, negative. So here we'd have a constant A. Okay. And this would be, for this velocity versus time graph, our acceleration would be positive, but it would be constant as well. There we go. So that's what it would look like. So here we'd have parabolic, quadratic, a linear, and a constant. So an example would be if you had like 10 y equals 10x squared. Go back. Let's say we have y equals 10t squared minus 5t plus 3. Then this, my velocity curve, would be 20t minus 5 And my acceleration curve would be 20. Okay, it would be just a constant value. And this would be my velocity, and this would be my acceleration. So that's an example of how it works with your equations. Okay, so we're going to explore that in some detail. The next big review you would need is remembering your kinematic equations. And how to apply. Okay, so we got 4 main equations we can use, and they all come from the definitions. So in our case, we have V equals V naught plus AT. So here's your final velocity, initial velocity, your acceleration times time. 2, we have delta x equals V naught. I usually use delta R, V naught T, or delta T. Plus 1/2 A delta T squared. That's a very common one. 3, we have V squared plus V naught. V squared equals V naught squared. So final velocity squared equals initial velocity squared plus 2A delta x. Okay. And the fourth equation is delta x plus 1/2 V plus V naught delta t. So these are the main 4 kinematic equations. And what you do is, this is all with reference to a horizontal x-axis. Now this could be all changed to your position, x values could be changed to y if you're dealing with a vertical height, or any other value. I like to use r a lot, okay? So here's your 4 kinematic equations. Most of the time you're looking for what variables do I have, what variables do I need to solve for. And these can only be used, this is only for constant acceleration. If you don't have constant acceleration, you cannot use these. So constant acceleration is 0. Acceleration is any value, like acceleration due to gravity, 9.8 meters per second every second, 9.8 meters per second squared. That's an example. Or maybe your car is changing its velocity at a constant rate. You're going from 10 kilometers an hour to 20 kilometers an hour in the same increment of time. You go 30 kilometers per hour. So that would reflect constant acceleration. So that means that the velocity changes linearly as a function of time. So that is something else to be proficient with. And the other part is your vector diagrams. Try to understand the vector notation of the motion. Try to represent the motion in terms of vectors. It's really important for you to picture the vectors, which are different than the function graphs that we were doing earlier. So vector diagrams are important. So vectors, what we want to do is represent the magnitude and the direction with a vector. Okay, that's how a vector is different than just a scalar. And when we're dealing with motion, let's say we drop an object, again like the ball, what does this vector, what would this vector diagram look like? So here's an example for drops with A equal to D, the acceleration due to gravity only. Okay, so if I were to drop a ball, so here's my y final value, or my y initial, which I need to it just depends on what textbook or reference you're looking at. There's two ways of doing it. Or I could say why and why not. Why and why not? Okay, so here's my final position, my initial position. So if I drop an object, like a ball from this height, how would I reflect this vectorially? So the motion, what's going to happen is the velocity at the top, v naught equals 0, and what would happen is it would accelerate due to gravity. So my position vectors would get larger as it drops. Okay, so here we have, let's say, y1. This is a y1 vector, y2 vector, y3 vectors. My vectors will continue to get larger as it drops and strikes the ground. And I want to represent that in my vector diagram. Okay, so I can see that there's a change in the position, and that change in the position vector will allow me to find the velocity. Okay? So if I were to drop an object, I would notice that it would speed up as it's dropped, right? So here I'm dropping it. So how do I represent that with velocity vectors? So in this case, I want to see how the velocity is changing, and my hunch is the velocity should change linearly as a function of time. So what's going to happen is my first vector is going to be a little small, I'll call that v1, and v naught equals 0 at the very top, okay? And it slowly increases, okay? Speeds up and it hits the ground. So there's velocity 1 vector, velocity 2, velocity 3, and we have little hats on these to represent vectors, or other ways of representing the vectors with dots. Okay, so here we have our velocity, reflecting our change in velocity as it hits the ground. So the way this changes should be at a linear rate. Okay, and we could graph that and we could get our acceleration values. Now, if we look at the other situation where we throw up, and it comes back down. Curious thing, when you throw something up, it comes back down, unless you're in the absence of gravitational field. So if we're way out in space and we have nothing pulling on us, then we could throw something up and it just won't come back. Also the case when you're sending things into orbit, right? If we want to get a rocket off the surface of the Earth and we don't want it to come back down, we have to go to a escape velocity, initial velocity that's incredibly high to get it up. Okay, but for the most part, we throw something up, it comes back down, right? Okay, so no escape velocity there. I don't have that much of a good throw hand. So in this case, we would represent very similar, okay, graph y, why not, y and why not. So what's going to happen is now we're going to throw it up. And we're going to start with a pretty high velocity, so it's going to go up. Go up some more, and then it's going to slow down as it hits the top and get to v top, which equals 0. And then the curious thing happens where it comes back down and hits the ground. Okay? And this whole time it goes from here to here, t equals your time of flight. And the difference between these vectors, so if this is v1, v2, v3, so delta v would equal v2 minus v1, and then you would also go v3 minus v2, and then on the way this is going upwards, and then delta v down would be, let's say v1, v2, v3, we'd say v2 minus v1 again, v3 minus v2, but I switched the order and we'd expect negatives. Now remember, these are vectors, so they have hats. We want to indicate their vectors. Okay, and always know in the context. So I've said it, and it should be known in the context and how I'm using it. All right, that's it. So remember those fundamentals and get started, and we'll see you soon.